Okay, this is going to be very quick summary, and my quicks are never that quick, about discrete sequences and series. Okay, so I'm also going to send you this page, although you could screenshot it for those of you who care. I don't know if any of you care. You could screenshot it, and I'll scroll down and keep a summary. And some of it's really important, some of it's not. So this chapter is going to deal with arithmetic sequences, sometimes called well, I don't actually, it's always arithmetic. And then there's geometric sequences, which I'll cover. These are covered but not as important because they're difficult to interpret, recursive sequences, but they deal with them. And then they talk about the sum of an arithmetic sequence. And what is an arithmetic sequence? It's a series of numbers that go up by a certain amount. What is a geometric sequence? It's a series of numbers that go up by a certain amount as well. This is the numbers added to it each time, and this is the numbers multiplied by it each time, but I'll get into more details. But a series is simply the sum of that sequence. So for instance, if I have 1, 4, 7, 10, it's clear these are going up by 3 each time. That means 3 is being added. If 3 is being added each time, it's an arithmetic sequence. If I was to come up with the sum of this, I would have to say, okay, I have 4 terms, and I'll plug it into this formula. I know the first term. I know the difference is 3. And I'll come up with a sum of, it's easy, I can see the sum here is 22. But when you put it into this formula, you should get 22 as well. A geometric sequence looks like this. It's clear that these are going up by multiples of 3. It's 3 times 1. 3 times 3 is 9. 3 times 9 is 27. 3 times 27 is 81. Because they're going up by multiples of 3 instead of additions of 3, it doesn't matter if the 3 is just an example. It's a geometric series and will fit within this definition and these formulas. And so sequence, geometric sequence. So these are called sequences. Each thing is called a term. Same with an arithmetic sequence. Each thing is called a term. The first term is sometimes called T1 or A. For arithmetic sequences, the amount they're added each time is called the difference. And for geometric sequences, the amount they're multiplied by each time is called the ratio. Arithmetic sequences are very similar to lines or simple interest, which you'll learn next chapter. They're totally related. And geometric sequences are related to either growth curves or decay curves, and to compound interest, which you'll learn next chapter. So it's important to learn these. So these are just how to figure out any term in the sequence, and these are used to sum up the sequence. And finally, the other most important thing in this chapter, which turns out to be very important, is Pascal's triangle. Very quickly, you can see that it's 1 all the way out on the outside on both sides. And it's clear that on the first row goes 1, 1, 1. Where do these numbers come up? They're the addition of the two numbers above it. So 3 is 1 and 2, and 3 here is 2 and 1. And the 4 here is the 1 and the 3. The 6 here is the 3 and the 3. It turns out that this is a very useful way to do an expansion. For instance, we learned that if I expand, let's use a and b. If I expand a plus b squared, let's get that a little bit bigger, a plus b squared in a bracket, and sorry, it's all comes out funny, that it's equal to a squared plus 2ab plus b squared. Now I'm just going to put a number because it's an invisible number in front of those, and I'm going to put the squares, squared here and squared here. But I want you to pay close attention to the number. It goes 1, 2, 1. We'll find that right over there. It turns out that if I expand this to a cubed, I'm going to get this, and I'm going to use the triangle now. So a cubed should be this next row here. I'm going to get rid of all this. And let's see if you can spot the pattern. Now, it's easier when they're all added like this, and I just have a term like AB. But it's going to be 1a, and this is for cubed. Keep in mind that we're cubing this one. It's going to be 1a cubed. And you might say, what about the b? Well, technically there's a b there, and it's b to the 0. But we don't do b to the 0. b to the 0 is 1. And then we have plus 3. Hang on. And then the a goes down by 1. It goes from a cubed to a squared. And sorry, this is finicky. And suddenly the b appears, and the b has a power of 1. And then we have a plus here. And then there's that 3. And the a is still around, but it's gone down from a squared to just a to the power of 1. And the b has gone up to the power of 2. And then finally this last one, which I'm going to rewrite or just move it here, there we go, is still a plus. The a is to the 0, it's essentially disappeared, and the b is 3. So what's interesting is when you see this, and you can confirm this in your symbol lab or you can expand this yourself, but this is a much faster way for me to come up with any expansion. And if these numbers change, I just plug them in to where I see them and be sure to apply the proper exponent. More on that little bit, but this becomes a very useful tool for doing huge expansions. Like this to the power of 7 is annoying, but not when we have the pyramid. And you might say, well, this pyramid only has 5 rows, but keep in mind it keeps going on forever that way. And then next year you even learn a formula where you don't have to use this pyramid, but it's based on the pyramid. And it's called Pascal because the guy who discovered it's Pascal. But this becomes a very simple way for me to expand things quickly. And math is all about finding quicker ways to do things. But let's go back to the very top. And I just want to get rid of all that so that I don't have anything on my drawing. We're going to go back to the very top and we're going to look at a couple sequences and how to spot them. So if you're given something like this, the best thing you can do is find the first differences. And by the way, if you haven't learned first differences, it's an incredibly important tool. So I urge you to study first differences because you can figure out many, many equations from first differences. But what are first differences? Well, first make sure that your x's are going up by 1. In some cases, these are not. And now I'm going to look at 18 to 23. How did I get there? Well, it looks like it went up by plus 5. And 23 to 28 looks like it went up by plus 5. And what you do is you take this term and subtract the term before it to see if you're dealing with an arithmetic sequences. Because arithmetic sequences are adding, arithmetic, adding. So this goes up by plus 5. It's quickly clear to me that all these things are going up by plus 5. That means I found the first difference. The first difference is 5. So that will instantly tell me, oh, we're dealing with an arithmetic sequence. So I know that the first term, in this case, terms actually, yeah, I should use the x is equal to 1 for the first term. But technically, term 1 in this case is 18. And I know each time I add 5, which means term 2 is going to be term 1 plus 5, which is 23. I now have a predictive way of figuring out all the terms. But, you know, I can't keep adding 5 to come up with the next term. And so, like, term 3 is equal to term 2 plus 5. But remember that term 2 that I just showed you was equal to term 1 plus 5. And soon I discover, okay, I have this thing where these 5s keep getting added. And it's really, I'm adding term 1 plus the difference that I find times n, and this in this case n is 3, the third term. N is which term number am I dealing with? Minus 1, which means in this case, if I want to find term 3, I take term 1 up above, which was 18. I know that if I multiply 5, the term I'm looking for is term 3. 3 minus 1 is 2. 2 times 5 is 10. 10 plus 18 is 28. And if I look at the chart, and don't be careful now because I've renumbered the terms like this. This first one of x is 1. So this next one's 2. And this next one here with a 2 in front of it is the third term. But if I look carefully, I'll see, sure enough, the third term, 1, 2, 3, is here. Now if I wanted, I could ignore this 0, because most sequences start with 1. So the first term, just to let you know, it doesn't start with x. But all they're doing here is training you on first differences, so they're using the old formulas. But anyway, you can see that I have a predictive way of coming up with it. And if you didn't catch that, that's okay, because I'm going to do more of it. Let's look at this one here. First of all, I need to look and say, wait a minute. These are going up by 6, not by 1. So this is going to be a bit more difficult. So this is clearly going up plus 6. And this here is going up by plus 12. Now the good news is the x's are going up by the same value. so it's still useful. And then this one's going up by 24. Well, first differences are not the same. This next one's going up by 36. So since first differences are not the same, if we keep going, we learn the same pattern in the second differences. So they're not really going to help me to do second and third differences. But we do know that when you have a repeating pattern like this, we're dealing with a growth curve, or in this case, since geometric curves are very much like growth curves, we're dealing with a geometric curve. We just need to figure out what number is being multiplied each time from the previous thing. Well, to do that, you take one term and divide it by the previous term. So 12 divided by 6 is 2. 24 divided by 12 is 12. Or sorry, 2. 48 divided by 24 is 2. 90. So we see this repeating pattern of 2. So in other words, if you don't have a first difference that's consistent, it's not arithmetic, move on to geometric. If you see this repeating pattern of the numbers in all the differences, it's probably geometric. Take this one term and divide it by the previous and see if that pattern holds up. Well, the pattern holds up here. I've discovered, by the way, the 5 I discovered over here is called the difference, 5. But over here I've discovered a multiplier of 2. This is called my ratio, or R for short. And my R in this case is 2. Well, if I look very carefully, my first term, let's just call the 0 of x the first term. Let's renumber these and just call them 1. And the size is too big, of course, but we'll just go for it. We're going to go 1, 2, 3, 4, all the way down. It'll make our life easier. Just like that. Okay. So that means my first term, term 1, and notice that you put the term here, doesn't really mean anything, just tells me which term I'm talking about, is 6. So that's my first term. I know my ratio is 2, which means term 2 is going to be equal to term 1 times my ratio, or times 2, and term 1 is 6. So that means term 2 is 12. Looking up, sure enough, it is. So I'm just going to keep that there. It's 2 times term 1. Term 3 is equal to term 2 times my ratio. Sorry, ratio times term 1. Term 1 times the ratio. Term 3 is term 2 times the ratio. I've discovered before that term 2 is 12, and my ratio is 2, so term 3 is 24. Looking up, that's correct. But let's keep it like this. So if term 3 is 2 times the ratio, but term 2 here is this, if term 2 here is that, I can replace this with term 2. And I can see I've got term 1 times the ratio twice. It turns out that term 4 is equal to term 1 times the ratio 3 times. Term 5 is equal to term 1 times the ratio 4 times. What's the connection between the number of times I'm writing the ratio and the terms? Well, this is term 5, and I've written the ratio 4 times. This is term 4, and I've written ratio 3 times. This is term 3, and I've written ratio 2 times. Which means an overall formula would be any term I'm looking for, which is written like this, is equal to the first term, which is sometimes written as A. Term 1 and A are interchangeable, times the ratio to the power. By the way, what happens when I have multiplied R times R times R here? It's R to the 4. What happens when I have R times R times R 3 times? It's R to the 3, R to the 2, just R. So it turns out if I put the ratio, the exponent up here, it'll be n, whatever term I'm looking for, minus 1. Let's give an example of that. Term 6, which is not here, will be equal to term 1 times the ratio to the power of 6 minus 1. What's 6 minus 1? 5. What's my ratio? 2. What's 2 to the power of 5? 2 times 2 is 4, times 2 is 8, times 2 is 16, 32. 32 is 2 to the 5. What's my first term? 6. So that means 6 times 32 will be my sixth term. 6 times 32. This is my sixth term. So we have a method, and it's written down on the formulas, and I'm going to do more of it, to find out any term in the sequence based on this formula. So those are the two big formulas. First of all, let's make sure x is going up by the same amount. Sure. That's going up by 2 here. Oh my God, it's jumping to 6. Oh, it's jumping to 10. It's jumping to, looks like 14. Let's take the second differences and see if there's anything there. I got 4. I got this is 10. 4. I've got something interesting. 4. So these second differences tells me it's not a geometric and it's not a arithmetic because the second differences are all the same. So that means I'm dealing with some sort of parabola. So if I look at this one, I've got to achieve a 5. So if I'm dealing with a parabola, I know that y, or whatever I'm looking for, is equal to x squared, because the second differences were all the same, plus some unknown number, called c, let's say. But if I look up, I can see that when x is 0, y is 5. So that means there must be this in here. Okay, let's see if I stumbled upon the formula. When x is 0 and I add it squared, add 5, I get 5. That matches up above. When x is 1, though, and I square it, it's 1, and I add 5, it's 6. That does not match up above. When 2 gets squared, it's 4. When I add 5, it's 9. That does not add up above, which means there's probably some multiplier in front. If I had to guess off the top of my head, I'm just going to put a 2 in front here. 2. So when x is 0, this whole thing becomes 0. It becomes 5. Check. When x is 1 and I square it, times 2 is 2. And when I add 5, it's 7. Check. When x is 3 and I square it, we've got problems in la-la land here. So now I have to see if there's any pattern that I can come up with that works. And this actual secret to coming up with the a that I did quickly is to write it out like this. Y is equal to ax squared plus bx plus c, and then use 3 numbers to slowly figure out a, b, and c. But I'm not going to do that here because this thing is all about arithmetic sequences, and that is not. But I'm teaching you how you would find out if it's an arithmetic sequence or not. For instance, this one has 1, then it goes up to 3, then it goes up to 5. They're clearly increasing by 2 squares. I'm adding 2 squares each time. Since I'm adding something each time, it's an arithmetic sequence. And the book continues to go through this to teach you how to figure it out. But the best thing to do is to take first differences right there. So you can see this one can go down, doesn't always go up. The first term's 18, goes down by 11, then goes down by 4, then down to minus 3, and the first difference is subtracting 7 each time. Since I'm subtracting, this is an arithmetic sequence, and this arithmetic sequence means that my difference is minus 7. So now we're going to look at this one. So, since I figured, so what were my steps? Figure out if it's arithmetic or geometric by first or more differences. If first differences are the same, it's an arithmetic. You can stop. Since we've had first differences are the same here, it's an arithmetic. We can stop. What's my first term? Well, I just got to look up here. First of all, do my x's go up by 1? My terms go up by 1? Yes. What's my first term? Well, term 1, which is also called a, is 18 in this case. My difference, which I've discovered, is minus 7. It's clear to me that term 2 is going to be term a plus the difference. And you might say, no, it's minus the difference. But when I put my actual difference in there, this becomes a plus-minus situation, and it works out. Okay, so always just keep it plus the difference in a bracket, and if the difference is minus, it'll change this sign. And term 3 is equal to term 2 plus the difference. That's how arithmetic sequence always work. It's the previous term plus the difference. Term 4 is equal to term 3 plus the difference. But right here, I have a definition of term 3, which means down here, if I put this in brackets, I can replace it with what term 3 is equal to. It's equal to term 2 plus the difference. So that means term 4 is term 2 plus 2 differences. And since I have a formula right up here for term 2, I can take that, and wherever I see term 2 here, I can put in a bracket and replace it with my definition up above of term 2. So suddenly I have a definition that's related to term 1, which works great. How many D's are there? There's 3 D's. What about here? Well, term 3 would be equal to, if I replace term 2 here with the definition up above, it's term 1 plus 2 D's. Term 2 is clearly term 1 plus 1 D. And I see a pattern. 3 as it relates to 4, fourth term is 1 less. Looking for the third term, 2 is 1 less. Looking for the second term, I multiply the difference by 1. So I have this formula. Any term I'm looking for, called term n, is equal to the first term plus 1 less than the term I'm looking at times the difference. Let's look at an example. Term 10 would be equal to term 1 plus, what term am I looking for? 10 minus 1 times the difference. Now, you can even do a weird thing here where you expand it, but I'm not going to do that just yet. I'm just going to fill it out. Well, up above I know term 1 is 18. I know 10 minus 1 is 9. And I know my difference up above is minus 7. Notice that the minus takes care of itself here. That means term 10 is equal to 18 minus 56. Did I get that right? 27, 54. No, I didn't. 63. I hate stumbling like that. And that means term 10 is equal to 18 minus 63, which is 18 minus, it's minus 45. So you could do it the long way and confirm that and just keep subtracting 7 up here over and over again. So minus 7, minus 10, minus 7, minus 17, minus 7, minus 24, minus 7, minus 34, minus 7, minus 41. Oh, did I get that wrong? I might have got it wrong. 18, 27, 54. No, it's minus 63. First term is indeed 18. So let's do it the old-fashioned way. Term 5 is going to be minus 10. Term 6 is going to be minus 17. Term 7 is minus 24. Term 8, 7 off, minus 31. Term 9, minus 30. Am I doing the differences right? Yeah, 38. And finally, term 10, minus 45. There we go. I did get it right. So almost drove myself crazy there. So now we have a formula in which I can figure out any term in the sequence. The secret is going to be they're eventually going to not tell you the first term. They're going to tell you like the 10th term and the difference, but they're not going to tell you the first term. So I'll give you an example. What if I knew the 10th term, as I do now, is minus 45? Let's say I didn't know the first term, but I knew the difference was minus 7. Well, I can still plug that into the formula. Tn is equal to the first term plus the difference times n minus 1. So if I'm looking for the 10th term, it would be T1 plus the difference times 10 minus 1 times 9, 9d. Well, they gave me the 10th term up above. It's minus 45. They didn't give me term 1, but they did give me the difference, minus 7. Minus 7 times this is minus 63, like that. And now all I have to do is solve for term 1. I add 63 to both sides, and I get this. So that's what they're going to do. They're also going to do weird stuff where they give you, let's look at this. They're going to tell you term 2 is 11. And they're going to tell you term 4 is minus 3. And they're going to tell you it's an arithmetic sequence, but they're not going to tell you the difference. Well, in this case, since these are two numbers apart, two terms apart, 2 to 4, there's going to be two differences in there. In other words, term 4 is equal to term 3 plus the difference. And term 3 is equal to term 2 plus the difference. Well, they gave you term 2 up above, and I can now up here replace term 3 with the definition I just created below, plus 2 differences. So term 4 is going to be term 2 plus 2 differences. Well, they gave me term 4, and they gave me term 2, and I know this is plus 2d. So all I have to do is use my arithmetic, subtract 11 from both sides. I get 3 minus 11 over here. I get minus 14 is equal to 2d. I get d is equal to minus 7. Boom, I figured out my difference. Now I just have to go back and say term n is equal to term 1 plus whatever, and I use minus 1 times my difference. I know my difference now is minus 7. If I use either of the terms up above, I'll use term 2, and 2 minus 1 here is this, so it just becomes plus minus 7, or minus 7. Since I know term 2 from up above, they told me term 2 is equal to 11, I can figure out by adding 7 to both sides that term 1 is 18. So the challenge is that they're going to be giving you more and more ways of doing it. And I'm not going to go through it all here. That's what these questions are about. They summarize the whole definition, that any term is equal to the last term plus the difference. And one term is equal to the previous term plus the difference, and any term is equal to the first term, sometimes called A, plus n minus 1 times the difference. But I've written it on that chart. We're going to go over it more. This is just a summary. And then they just give you challenges. So your challenge is just to see if you can figure out if this is arithmetic or not. And I'm not going to do all these because that's not what this section about. This is about just discussing arithmetic sequences. But I'm going to look at them. And sometimes it helps if you just put them vertically and you put them with their terms. So we go term 1, 2, 3, 4, 5. And then the numbers they've given me on the left are term 1 is 1, 5, 9, 13, and 17. So you can see that what I've done is I've made it horizontal up here. I've put this thing, as soon as things work out for me here, I put this thing vertically. And this allows me to say, okay, well, that's going up by plus 4. And yeah, you could do it horizontally, but it helps me to see the terms too. This is going up by plus 4, plus 4, plus 4. Immediately, because they're all the same number, I know this is an arithmetic sequence. I also know the difference is plus 4. I also know the first term, term 1, which is equal to A, is equal to 1. They sometimes call the first term A. Using my knowledge of the arithmetic sequence, term 2 is going to be term 1 plus the difference. Since I know term 1 is 1 and difference is 4, I would just write it like that. I wouldn't keep in. Actually, you know what? I think I would write the blank one first. Then for full marks, you would leave term 1 in there and just do 4. But you can also do, I believe, they would want it like. Oh yeah, you should. Yeah, this is the recursive. Term 1 is, you can also write it as that. But I think they just want it with the blank where you fill in the difference. I don't think they want you to fill in the term 1. I'm going to get back to that. If I want to figure out what's called the general formula, term 2 is equal to term 1. I won't do general. I'm just going to take the formula, which I know is term 1 plus n minus 1 times the difference. I know that we would just leave this like this. And I know term 1 is 1. And my difference is 4. And there I have now a method to figure out any term that I want. You can even expand this. So I'm going to put the 4 in front. You could even expand this. Term n is equal to 1. What's 4 times n? 4n. What's 4 times minus 1? Minus 4. What's 1 minus 4? Oh, sorry, this is 4n. Can't subtract these, but I can put the minus 4 over here. What's 1 minus 4? Term n is equal to minus 3 plus 4n. You can see that either of these formulas, one is the expanded version. Technically, this is the general term formula, but this is an expanded version that's sometimes faster to use, and that way I'm not just subtracting something over and over and over again. So that's what they want you to do here. They want you to figure out and you'll look at the sheet, we'll go over more what the general term and recursive formula is, and then they just keep challenging you over and over again. This goes up by 3, 3, 3, therefore it's arithmetic. This goes up by 1, 2, and then 1, it is not arithmetic because it didn't go up by the same thing. 3, 6, 12. No, that's going to turn out to be geometric. 11, 11, 11. Yes, that's arithmetic. And sometimes you can see even, oh, what about this one? That's 12, 12, yes. Oh, 14 rather. 14, 14, yes. Goes down by 4, goes down by 4. Arithmetic. And then they want us to come up with the formula, which we will. Again, this is not about answering all these questions just yet. You can even have stuff like this, and when you're presented with a fraction and you don't know how to go about it just by visually looking at it, always remember, if you're told, or if you're trying to figure out it's an arithmetic or not, take one term and start by subtracting the previous term. So what is a third minus the previous term? A sixth. So I took this term and I subtracted that term. Well, I'd have to put them on the same scale. Well, this is 2 over 6. So I get a difference of 1 over 6. If the next one also is 1 over 6, I know that I've probably got an arithmetic sequence. So now I'm going to take a half and I'm going to subtract the term before it, which is a third. I have to cross multiply to get these over 6. So when I multiply this by 3, I get 3 over 6. When I multiply this by 2, I get 2 over 6. 3 over 6 minus 2 over 6 is 1 over 6. So if I do the next one, 2/3 minus a half, well, I get 1 over 6, 2/3 minus a half. I have to cross multiply them again. This becomes 4 over 6 minus 3 over 6, which is 1 over 6. So since they're all going up by 1 over 6, I know that it is indeed an arithmetic sequence because it went up. I also know that the second term is equal to the first term plus the difference, which is 1 over 6. I also know that any term I'm looking for is equal to the first term plus 1 less than the term I'm looking for times the difference, which is 1 over 6. And I also know the first term up above is 1 over 6. So now I have a formula here to figure out any term. If I want to figure out the fifth term, I would just put 5 minus 1 over here. It's 4. 4 times the 6 is 4 over 6. 6 plus 4 over 6. Term 5 is equal to 5 over 6. So you can figure out anything. Once you determine it's arithmetic, it will follow the formula given. So, moving on, let's have a look. So that's the test it wants. Now let's look at geometric sequences. How do we spot a geometric? Okay, let's look at these. And remember, this is not about covering everything. This is just summarizing. So, geometric sequence. How do I figure out if these are geometric? Now, I never like when they're sideways, but we'll work with them sideways. Always just take the first term and subtract the left term to start. This goes up by 9. 36 minus 18. Oh, it's going up by 18. 36 up to 72 is 36. And it's almost a hint there. I can see these are each going up by 2 multipliers. I immediately know that's not an arithmetic. So now I take one term and divide it by the term before. 18 divided by 9, 2. 36 divided by 18, 2. 72 divided by 36, 2. Suddenly, since I see this multiplier, I know that we're dealing instantly. Geometric. Just say geometric right away. Because we can see they're multiplied by a number over and over again. Term 2 is going to be equal to term 1 times my ratio. I've just figured out my ratio is 2. It says term 1 is 9. So let's see if that's true. Is term 2 18? Yes, it is. Term 3 is going to be equal to term 2 times my ratio, which is 2. Term 2 is 18. 36. Yes, that works. However, I don't want to keep doing that. And term 2 is going to be equal to term 1 times the ratio. And term 3 is going to be equal to term 2 times the ratio. And term 4 is going to be equal to term 3 times the ratio. And term 5 is going to be equal to term 4 times the ratio. I can do this. Well, right here I have an equivalent for term 4, which means down here I can put in brackets and put in that equivalent. Great. Which means it's term 5 is term 3 times r, which is r squared, isn't it? R squared. Well, it turns out that I also have a definition for term 3 up above. I can replace term 3 with what I see up above. It's r squared here. Term 3 up above says it's term 2 plus r. So now I have term 2. Oh, and sorry, it's not plus r, it's times r. So let's do that again. I can replace it with what I see up above, which is term 2 times r, and don't forget that it's times r squared. Well, I quickly see that term 5 is equal to term 2 times r cubed. And finally, I can replace that term 2 up above with an equation is equal to term 1 times r is what term 2 is equal to, times r cubed. And suddenly I see that term 5 is equal to term 1 times r to the 4, which is where we've come up with this equation. Any term I'm looking for is equal to the first term times the r to the exponent of whatever term I'm looking for minus 1. Let's see if that works. We've got term 7 over here. We know what it is. Let's just see if the formula works. So if I'm looking for term 7, I'm going to take term 1, I'm going to multiply by r, and it's going to be to the power of 7 minus 1. 7 minus 1 is 6. Okay, that means term 7 is equal to term 1, which I know is 9, times r, which I know is 2, to the power of 6. All I have to do is figure out what 2 to the power of 6 is and multiply it by 9. 2 to the power of 6 is 64, and times 9 is 576, which means term 7 should be equal to 576. And sure enough, it is. This is the formula. And again, what they're going to start doing is giving you just term 7 and giving you term 1. And they're going to give you the ratio in term 7, and you got to figure out term 1 by moving backwards. And sometimes they're going to do this. They're going to give you, let's say they're going to tell you this is a geometric sequence so that you know it has r. They're going to tell you term 2 is equal to 18, like it is. Term 5 is equal to 144. Well, you know that term 5 is equal to term 4 times the ratio. But you know that term 4 is equal to term 3 times the ratio. And term 3 is equal to term 2 times the ratio. In other words, you know that term 5 is equal to the ratio times term 5 is equal to term 2 times the ratio cubed. Well, they gave you term 5, and they gave you term 2. You just don't know the ratio. You do know it's got a ratio because they told you it was a geometric sequence, which means r cubed is going to be equal to 144 divided by 18. All I have to do is figure out what 144 divided by 18 is. It's 8, which means if r cubed is equal to 8, r, and this is a very careful thing you have to do, r is equal to plus 2. Now, if it had come out as r squared is equal to 4, you must be very careful here because the possible ratios are r is equal to 2 or r is equal to minus 2, and you must investigate both to see if it works. Sometimes there's a few tricks in these things. And you just have to remember that r squared, or anything to an even exponent, has a positive or minus answer. When it's cubed, or to the 5, or to the 7, or to the 9, it's always going to be exactly what works. You don't have two possible answers. So that means I know now my r is 8. I still don't know my first term. However, I do know the general formula is term n is equal to term 1 times r to the power of n minus 1. They've also given me already term 2. So term 2 is equal to term 1 times r to the power of 2 minus 1, r to the power of 1. They've given me term 2. I figured out in the last step r, which means term 1 is equal to 18 divided by 2, and now I know the full formula. I now know term 1 is equal to 9, r is equal to 2, so I can write the general formula. Like that. So it might be going fast, but you'll get it. One just follows multiplier rules, one follows an addition rule. They just give it harder and harder questions, and keep in mind that it can go negative. You're always just going to take the one term and divide it by the previous term to figure it out. And they make you do the same thing. They want you to figure out if you can figure out if it's arithmetic or geometric. Creating rules to define sequence. So sometimes they don't follow this rule. But what they want you to do is learn how to study the first and second differences to figure things out. For instance, I'm going to show you something here. It's very easy to see that, so we can see this here, right? Okay, well, let's look at what they did exactly. That might be even better, because this is a good example of how sort of depth of thought you have to have, right? So I'm going to start with this one up top. And I'm just going to cut it down so that we can have all on one page. Yep. So if I look carefully at this top one, I can say, okay, here's my first differences. That's going up 7, that's going up 8, that's going up 10. Then I take my second differences. I can say, okay, that's going up 1, that's going up 2, that's going up 1. And I could even take third differences here. And I can say, okay, everything's going up by 1. So I found third differences. By the way, that would indicate that it's an x to the cube, and it can be figured out. But what they're doing here is they're saying, well, if you know it's going up by 1 here, and it goes, as you can see, 1, 2, 3, you can predict that it's going to go up 4, 5, 6 as the second differences. And that means that you can now know that this one here is going to go up by 4, and you can predict it's going to be 17. And you know that this 17 is going to go up by 5, and you can predict that it's 22. But then you can use that and say, well, okay, if this is going up by 17, it's going to be 56 over here. And if this is going up by 22, it's going up to 78. In other words, you can once you find a definable first and second differences, you can work backwards to figure out the first differences and then to figure out the actual terms. And that's what they're teaching you here. But I also want you to keep in mind that sometimes they're going to get really tricky. And they're going to give you a so clearly we can see it because they do it in the book here. But they're going to be really tricky sometimes, and they're going to say, okay, see if you can figure this out. And they're going to just skip some numbers here and there. They're not going to give you that either. Skip that. I'm going to skip that. And they might even, when they do that, they might even do that. Heck, they might even stop like that. And they're going to ask you to fill in this table. And you're going to say, okay, well, third differences here are 1. So it's clear. So that's clear. It's going to be 4 and 5. And they're also, keep in mind, they're going to skip a whole bunch of, maybe they're going to skip tons of numbers. But now that you have this information, you know that this one, so this one went up by 1, which means this went up by 2, which means that's a 10. And this one went up by 3, which means that's a 13. And this one went up by 4, which means that's a 17, which makes sense because this one went up by 5. And now I can go backwards and say, well, if this first difference went up by 7, that's a 15. And if this next one went up by 8, that's a 23. And if this next one went up by 10, that's a 33. And then I have the 39. And you just want to, sometimes you got to make sure you took the right numbers. So I think I actually screwed that one up. So this one goes up by 7, the first difference, so it's going up to 8. Then it's going up by 8, so that's a 16. Then the 16 is going up by 10, so that's going to be a 26. And that makes more sense. And the 26 is going up by 13, 39. The 39 is going up by 17, 46, 56. And now I filled up all the table by sort of understanding first differences and second differences. Very, very useful skill. So be able to do first, second, third. And I could go into a formula because I figured out the first differences are 1. And that tells me that it's y is equal to ax cubed, because if the third differences are all the same, it's a cubed, plus bx squared plus cx plus d. And it would be great if they'd given me a 0 up here so I could figure out d. But they've given me enough. Here's the first term. And by the way, they're numbered over here. 1, 2, 3, 4. This is actually the numeric term that we're dealing with. This is the first term. This is the second term. This is the third term. This is the fourth term. Well, I know that that's essentially the x values, the number of terms. So I could actually figure it out like this. And I could say, well, I know for term 1, y, or the term actual term, is 1. So I could say a1 cubed, because that's the first term. Well, 1 cubed is 1. So 1 is going to be, and bx squared is 1. And when x is 1, x is that, 1. So it's going to be c plus d. So right away I know a plus b plus c is equal to d. Now looking at the next term, term 2, I know term 2 is equal to 8, and 2 cubed is 8. So it would be 8a, and 2 squared is 4, so 4b. And I'm just subbing it into the main equation. And term c is going to be 2c. And then term d I'm not going to know. But now I have an equation for this. And because I have an equation for this, and up here I can say, well, you know what? D is equal to 1 minus a minus b minus c. That's what d is equal to. So right away down here I can replace my d with 1 minus a, it's important to use brackets by the way, minus c, and now I don't have a term d in this formula. And I can keep going down and down and down until I solve for a, b, c. And I'll do a separate video. I think I already have, but it's a very important skill to have. Then moving on, it goes on about geometric sequences, but eventually they cover recursive. Now recursives are really weird. Recursives don't follow the arithmetic or the geometric rule, but they do have a pattern. Just the pattern is hard to figure out. So I'm going to write down some terms, 1, 2, 3, 4, 5 terms. You're going to see if you can see the pattern. Okay, 1, 4, 5, 9, and 14. And what the pattern is I'm going to give you term 1 is 1 and term 2 is 4, but term 3 is going to be equal to term 1 plus term 2. 4 plus 1, or sorry, 1 plus 4. So that means term 3 is that. Term 4 is going to be equal to term 3 plus term 2. Okay, well, term 3 is 5, term 2 is 4, so term 3 is 4, so term 4 is 9. So you can see what's weird about this one is this term depends on the addition of these two terms. And this term depends on the addition of these two terms. So it's not going to follow a recognizable pattern. And they deal with something that's called the Fibonacci sequence, in which term 1 and 2 are 1. But term 3 is equal to term 1 plus term 2, which is 3. Or 2, rather. And term 4 is equal to term 3 plus term 2, which is 3. And term 5 is equal to term 4 plus term 3. And term 4 is 3, and term 3 is 2, so it's 5. And it's going to go up like that over and over again, adding the last two terms. And what happens in this is you'll find that nature repeats this pattern, and you'll also see it represented a lot like this in blocks. So I have a block here, and then I have two blocks beside it of equal size that I can fit in beside. Or actually, do I do it in half? I think I do it in half. And then and I forget how the drawing works. I think they do it like this. 2 blocks, and then the next term's 3 blocks, something like that. Didn't quite get the blocks right. And then the next one's 5 blocks. I didn't get the blocks right. But what you get, and you should look up the videos, is you get this repeating swirl pattern called fractals, in which nature actually replicates the Fibonacci sequence. It's why he studied it. However, the Fibonacci sequence is not that big a deal. They just want you to understand its connection to biology. Then they jump to a series. A series is simply a way of adding up. So for instance, if I have this arithmetic series, which clearly goes up by 4 each time, instead of constantly figuring out how much it goes up, it's going up by 4, each time. Instead of adding all those over and over again, I want to come up with a theory or a formula to be able to add them. Yeah, I can add the first 3 sequences easy enough. It's 15. But as I get bigger and bigger, that chore becomes more and more. So they come up with a formula, and I'm not going to get into how they derive it. It's interesting how they derive it. It has a role. It'll have a role in simple interest, because this is how they came up with the simple interest formula too. And they just come up with a formula. And the formulas depend if you know the difference and how many terms and the first term, or if you just know the first and the last term, and therefore how many terms. So let's use both. Let's use the simplest one. By the way, how do they come up with this? Well, notice that this is 26 when I add them. And this is 26. And this is 26. And just this last one is the tough one. So sometimes if it's even, I can see that the first terms and the last terms and the second last and the second terms and the third last will all add up to the same number. And that's how they came up with this. But let's use this first formula. It says, how many terms do I have up here? I got 1, 2, 3, 4, 5, 6, 7. So my n is 7. What's the difference? Well, they're going up by 4. Difference 4. What's the first term? First term is 1. So a is equal to 1. So let's start with this one. This one, apparently the sum is going to be equal to the number of terms, 7. The first term, oh, I need the last term on this one. So the last term, sometimes called Tn, is 25. And I really don't know how many terms there are here. Well, I do. It's 7. So right away I can say, okay, well, it's going to be 7 times the first term, 1, plus the last term, 25, which is 26. And all of that, whatever I come up with, divided by 2. Okay, well, 7 times 26 divided by 2. Apparently, if I add up all the numbers up above, it will add up to 91. Let's try the other formula right here. Okay, well, this other formula says I need the first term and the number of terms. Okay, well, I know the number of terms. It's 7 times, open brackets, 2 times the first term, so 2 times 1, plus I'm dealing with 7 terms, so n minus 1 will be 7 minus 1, times the difference, which I know is 4. Now notice that second part looks a lot like the formula, and it's all going to be divided by 2, but we'll just leave that for now. And notice I got to resolve the brackets first, so I got 2 here plus 6 times 4. 6 times 4 is 24, so I get 26. Kind of what the first and last term add up to, isn't it? Then I have to multiply by the number of terms and divide by 2. Notice that this is the same formula as right here, so I don't need to come up with it. And this, they came up with that, or vice versa. They're connected. But notice the similarity right there of the actual how to find the sequence. And they really multiply by 2 to say essentially that we're taking the first and the last term added together. We're multiplying it by the number of terms, and we divide it by 2 because when I add 2 numbers together, I'm only going to get the actual value when I divide them by 2. But anyway, you don't have to know how it's derived right now, just the formula. And it's used, either one is used depending on what you know. But also keep in mind, they're going to do exactly what they did in every other chapter, in that they're not going to tell you all the information. For instance, so it was 26 divided by times 7 divided by 2. We know that the sum of this, 26 times 7 divided by 2. We know that the sum of this particular one is 91. So they might tell you, okay, well, the sum of these sequences is 91. And they might say, okay, and the first term is 1. And they might say, okay, well, the difference is 4. I think that was the one we came up with, 4. And they might say, okay, come up with the first term. So you'd have to plug it into the formula differently. Oh, we don't know how many terms, right? So, they might tell you the last term. So they might say the last term is, and now I wish I'd kept it around because I can't remember what I had. I think I had 1, 5, 9, 14, 13, 17, 21, 25, okay? And they tell you the last term is 25. Well, then you got to learn your sequences. So in this case, I could use the second one. No, I can't. I don't know the number of terms. And actually, they're going to do something tricky even. They're not going to tell you the first term. So you have to use your knowledge of the first recursive formula. Say, well, Tn is equal to the first term plus, and they might tell you, they're going to tell you, okay, well, n is equal to 7. There's 7 terms. And you're going to say, well, that Tn is going to be equal to T1 times the difference times n minus 1. I know the number of terms is 7, so 7 minus 1 is 6. They told me the difference is 4, so we're talking about 24. I know the last term they told me is 25, so really we're talking about 25 is equal to term 1 plus 24. It's clear that term 1 is equal to 1. Now that I figured out term 1, I can use this formula here. And I can figure out, what do I need to figure out? I actually don't need to figure out anything. If they didn't give me term 1, and I wanted to do it differently and didn't know the sequences, can I figure it out? I think they have to give you enough information, but my point is they're going to give you enough so that you have to figure out term 7. So in this case, we know the sum is 91. We know the number of terms is 7, but we don't know 2a. But we do know the number of terms, again, is 7 minus 1, so 6. And we know the difference is 4. 6 times 4 is 24. And we know it's all going to be divided by 2. Well, to solve this algebraically, we have to solve for a. So we're going to multiply both sides by 2. We get 182 is equal to 7 times 2a plus 24. I'm going to divide both sides by 7. So 182 divided by 7. And you get the idea. We're just going to bit by bit get this. 26 is equal to 2a plus 24. So 2a is equal to 2, which a is equal to 1. So they're going to reverse it each time. So the next one is about the same thing, but it's a geometric series formula. Much harder. And the geometric series formula I will not derive here, but if you're interested in, there is derivation online. And it uses, it's actually quite interesting how they come up with it, but it's not easy. They use the formula, I think they use the formula for a growth curve to come up with it. Because you learn that a geometric series is the same as a growth curve. And so they come up with this formula. The sum is equal to the first term times the ratio to the power of how many terms there are minus 1, all divided by the ratio minus 1. Very hard to visually understand where that came from. Or the sum is equal to term of the highest term, one above the highest term, minus the first term, divided by r minus 2. Now, it would be hard to figure out one above the highest term unless you know the ratio. So sometimes if you know that the last term is 25, and you know the ratio is 2, well, you'll know that term 20, let's say it's term 7 is 25, you'll know that term 8 is equal to 25 times that ratio, 2. So term 8 is 50. Well, term 8 is 1 more than the biggest term they give you, so you put that 50 in for here. Kind of hard to understand. I'm not going to go into great details, but essentially you're learning how to add up a big long sequence. That's what a series is, a formula to add up things in a geometric. And finally, to me, this is the most important one. This will teach you how to come up with binomial expansions like x plus y to the power of 4 using solely this pyramid. And it's a very useful pyramid to use to come up with any binomial formula. So your teacher's going to do something mean to you like this. She's going to say, what is, and she's going to make these harder than just x and y, by the way. She's going to say, what is this to the power 7? And you're going to have to go quickly, oh, I got to draw this pyramid. I could have actually drawn them a bit closer together there, on the first one anyway. And you're going to say, okay, I got to put a 1 on the outside each time. And I got to put a 1 on the outside each time. And a 1 on the outside each time. And I got to add up the middles. So it's clear that this one just goes like that. But this next one, there's a 3 there. And this next one here, there's a 4 and a 4. And this next one here, there's a 5. Here there's an 8 and a 5. And let's see, this is to the power 0. This is just to the power 1. That's to the power of 2. Sorry, I added that up. Those add up to 2. This is the power 3. This is to the power 4. We're trying to get to the power 7. So we get 1, 1. So I got to go even further. And I can say, okay, this is the power of 2. This is the power 3. This is the power 4. This is the power 5. And I get 6 here when I add up those. 13, 13, 6. And on the power of 6, I'm going to get 1. These add up to 7. 19, 26, 19, 7, and 1. And then finally the power 7, I'm going to get 1, 8, 26. Whew, gets pretty tough. 35, 45. Then it goes back down. 26, 8, and 1. Did I get them all? I think I got them all. So now that I know what the power 7 ratios are, or coefficients, and you're like, what are you doing? You'll get into it more when you learn it. I know that I'm dealing with 1, 8, 26, 45, 26, 8, and 1 as coefficients. I want to space them well out. Well out. And I might as well just do it like this. They're being added in that bracket, so I'm just going to put x, y with a bit of space plus. And this might be easier for you to see. X, y plus 26 xy plus 45 xy plus 26. And you're like, yikes, hurry up. Xy. Well, all of math is, I won't say tedious, but it requires the patience to explore. You might want to say that it's even the last exploration possible. So all I did was put an xy in front of each of them, right? That's all I did. So let me zoom in, make it easier. So that's what I'm going to focus on right now, just this part of it. Remember that we're doing x plus y to the power of 7 rather. And then you can say, well, what exponent do I put over them? Well, it's to the power of 7, so it's going to, for the x, it's going to go 7, 6, 5, 4, 3, 2. Oh, I missed one. See? I screwed up. So somewhere there's a there's a number in there. So I'm just going to do the coefficients because I screwed up. And that's what happens when you don't do the triangle properly, right? So I'm going to look up Pascal's triangle and get the right one. So what's number 7? That's the power 1. That's power 2, 3, 4, 5, 6, 7. So I missed two 35s in the middle. That's what I missed. So I did totally the wrong row, it looks like. Power of 2, power 3, power 4, power 5, power 6, power 7. Yeah, this is the row I should have used. And it has the 1, 7. And there's the indication right there. I should have looked for the 7. So this is the actual coefficients I should have used. Let's see if I can pull it up now here. And yeah, I would have taken my time and drawn the pyramid more accurately. So these are the actual coefficients. So I got the 1 right, but this has got to be a 7 here. And this has got to be a 21. And this has got to be a 35. And this has got to be a 35. And this has got to be a 27. 21 rather. And this has got to be a 7. And then finally the one I missed. There's one more. Plus 1xy. And as I said, I was going to power 4, to the power 3, to the power 2, to the power of 1. And this last one is power 0, which is just 1. So I get rid of it. Now, how do I number the y's? Well, I do the reverse. This is going to be the 7. This is going to be the 6. This is going to be the 5. This is going to be the 4. This is going to be to the 3. This one's going to be to the 2. This is going to be to the 1. And this last one's going to be to the 0, which is just 1. So I get rid of it. And I can get rid of one exponent or one coefficients too, because we never really write those. There we go. So suddenly I have an expansion of x plus y to the power of 7. Might not have seen that fast because I bumbled, but it was pretty fast. Which is x to the 7 plus 7x to the 6 y to the 1. And I can skip writing the 1. Plus 21x to the 5 y to the 2. Plus 35x to the 4 y to the 3. Plus 35x to the 3 y to the 4. Plus 21 times x to the squared y to the 5. Plus 7x to y to the 6 plus y to the 7. Notice that it always sort of starts with the first thing to the power and the last thing to this power. But the trick is going to be when they don't just give you x and y, they give you 3x plus, or let's say plus even minus 2y, all to the power 7. And the secret there is when I see x to the 7 here, right here, I can write it all out like this, but then I'm going to replace with x to the 7 with 3x to the 7, and I must put my 3 to the 7 and my x to the 7. Then over here with the y, I've got to replace it with minus 2y to the power of 1. That minus will make this plus a minus. This x to the 6 must be replaced with 3x, and I must put them both to the power of 6. So you can see all the coefficients are going to change, and I'm going to need more multiplying power. I'm going to have to do more to the power of 6's. But once I get this base down, I can substitute anything and figure it out much faster than trying to expand a power to the 7. Woof! That was a long video, but that's about it. Stop at any time.